This is a reverse osmosis pilot unit, and an engineer that's designing a full-scale system for a municipality would utilize this equipment in designing the system, the process design and chemical injections and other criteria for a successful full-scale system. If you just build a system without a pilot study, what can happen is that you don't necessarily address all the items that make a system efficient, and it can cost a lot of money to modify the equipment once it's built. So by doing an RO pilot, that an engineer can accurately identify all the process parameters to do a design that has the lowest O&M cost and the best life expectancy. So this RO unit represents the smallest RO unit that you can build that fully replicates a full-size system in all hydraulic criteria, chemical consumption per thousand, power consumption per thousand, cleaning frequencies, and membrane life. And all pilots are not necessarily equal depending on what kind of equipment comes with a pilot. And as I said, this is a very comprehensive pilot and uses unique equipment in order to identify those costs so you can accurately project what the operating and maintenance cost is going to be for the city. So Glenn is going to identify some of the criteria and process parameters of this system so it's fully understood what equipment is necessary in order to do an accurate pilot and to make an accurate full-scale design.
Hello, I'm Glenn Bradley from Harn R, Senior Field Technician. This is our RO pilot. Our standard RO pilot has 4 hydraulic connections, well inlet, well flush, permeate, and a concentrate. We also have a well booster pump over there if your well pressure is too low to supply our high pressure pump with adequate flow. This is our injection point here, 3 chemicals. We typically run acid, bisulfite, or antiscalant. This is our cartridge filter housing. Water then flows to our high pressure pump. We have various data acquisition points, temperature, conductivity, ORP if needed, and pH. We also have our interstage boost pump located on this end of the skid, used to increase second stage flux. Once water passes through our high pressure pump, it feeds these 2 3-element vessels. It wraps down around the other skid and comes back here in these 4-element vessels, first stage concentrate. The interstage boost pump takes the water, increases flow and pressure to increase flux through the second stage feed, second stage elements, which are located here. This is second stage feed, which also wraps down around the other end of the skid. This is second stage concentrate here. We control concentrate flow by this valve here. Our pilot takes 480 volt supply, which is supplied to this cabinet here. We also have a power meter here that monitors your hour watts, or your watt hours rather, so engineers can take that information and determine overall cost for power consumption. This is our HMI, or user interface. This pilot is run by a computer. There are various user adjustment set points in here, and then there are also hard-coded points in here that cannot be adjusted. All of our data is data log here, which can be accessed via air card or downloaded by the engineer if need be at the end of the pilot or in real time. This is our water wet panel, if you will. We have various redundancy with pressure transducers and pressure gauges. We also have sample valves for every individual vessel, interstages, and permeates. We also have the ability to blend raw water to increase capacity or permeate capacity.
We have a full information package for these units that it has in detail all the equipment that's supplied with the unit.